This is my friend. This is my electrical resistance tomographic system. That means that this box here is measuring how hard it is to pass an electric current through the ground, not just in one place, but all along this line of electrodes that we have here. And it has a switching system and a computer built in. So it starts by putting electrical current into the ground between two electrodes at the far end there, and measuring the potential, the voltage produced by that current at a pair of electrodes next to it a little bit further this way. And another pair, and another pair, and another pair, and another pair. 10 sets of electrodes doing the measuring, 2 putting the current into the ground. And then, once it's done one cycle of that, moving one space further along, and again, and again, and again, all the way to the end of the line. And having done that once, it does the same thing, but with twice the distance. So instead of one electrode and the next electrode putting the electrical current into the ground, it's 1 and 2 over. Again, all the way along the line. Why? Because by doing that, it's putting current into the ground that goes firstly near the surface because the electrodes are quite close together, and then, because the electrodes are a bit further apart, the current passes a bit more deep, and then further and further until it's as wide as it can get. By doing that, we're sampling the electrical resistivity of the ground to a certain depth. Here it's going to be 15-20 metres, probably a bit more, that kind of thing. It depends on the distribution of the resistivity itself. But by doing this, we're able to see down into the ground. The data we gather by doing that, we take back, and we run a process which we call inversion, which does some mathematical modelling to fit our picture of what we think might be under the ground to the measurements we made, and improve that model until they fit as well as possible together. So we can see the distribution of resistivities in the ground. And if I have compact rock, very dry, underneath me, overlain by a layer of wet clay, I'll have a resistive zone and a conductive zone, and this will allow me to see the difference between the two. Now here, that's incredibly valuable because we know we have this disturbed slip material. We know that we have water coming down into these hollows and from the top through and underneath this disturbed material, and then we have the undisturbed material underneath, slightly deformed, and there's a boundary between the two. So we're hoping that we might see a zone of disturbed material at the top which is relatively wet, conductive, certainly very variable, and then a zone where we may have water flow at the contact, and then compact material underneath. So 3 different resistive zones. If we're lucky, we might be able to determine that using this equipment. Now, this is absolutely standard civil engineering, geological, environmental, water quality survey equipment. And pieces of kit like this are very widely used for many purposes. Used in archaeology as well. I hope, if everything works out, that we're going to be taking this piece of equipment to the site of Medina Asahara, great palace site in southern Spain in May, and I'm going to be looking for the structures of the walls of the buried palace using the same equipment. So for archaeology as well, it's extremely valuable equipment. But it's good for doing vertical soundings quite slowly. You can see it's taking a long time to take its readings. In total, it's going to take a further, how long? 15 minutes, 20 minutes to do this particular set of measurements at least, perhaps a bit more. So it's a little slow, takes time to set out, and we have other methods, radar for example, magnetometry and so on, which allow us to do surveys more quickly, but this is one of the most flexible techniques we have. It works under many different circumstances. I've taken this out to the middle of very dry deserts, got very good results. We've used this particular kit up on rock glaciers in the Swiss Alps, looking through the surface rock to the ice mass in the centre and then to the rock underneath the glacier. So it's an incredibly valuable and flexible piece of equipment. We're doing measurements in 2 different ways here. One, as I described, using the electrodes at this end and then measuring away from it, and in another we have the current going in from wide electrodes and we're measuring the resistance through potential pair in the centre. We do this because they measure different zones. The second method goes deeper into the ground. We mix the data together back in the laboratory, in the computer memory, and then we do our inversions, our corrections using the whole lot together to get detail at the surface and detail at depth. So that's what we're going to be doing. It takes time. We'll probably do it maybe only here today since we have so many other things to do. We'll measure the topography and we'll work out where every electrode is using the GPS. It doesn't take long to do, because that's necessary to do corrections. You'll see, for example, it goes over a hill at that end. Because it's going over a hill, the electric current can't flow sideways through the ground because the hill's there, there's nothing sideways. And so the resistance is higher purely because the topography is different. That we have to take into account and correct for in our interpretation. But that's fine, we measure it, we introduce it into the mathematical model, and then we get a result at the end of it. And we'll see some of those results when I next talk to you about this work back in Liverpool and hydrological modelling as well, because we combine these physical models with hydrological models to try and understand the relationship between electrical conductivity and water flow.